Good afternoon, ladies and gentlemen. As you can tell, for Physics 30, I managed to get this the screen to be a little bigger. So I'm going to redo that. Actually, I'm going to do a new lab with you. The Physics 30 determining the wavelength of EMR Lab. Now, I'm supposed to do this in pairs, but congratulations, you're doing it on your own. So, question, what is the wavelength of red, green, and blue light? Well, those of you that can read are going, red light is somewhere around 750 nanometers, 610 to 750. And make a note, the red laser we're using is 650 nanometers. Then we're asking, what about green light? Well, green light is somewhere around 500 to 570, depending on who does the definition. And note here, this green laser is 532 nanometers. And finally, blue is somewhere around 450 to 500, depending on who does the definition. And the person who did this says it's 405. So this this blue laser is 405 nanometers, so it's technically more of a violet. But as I explained earlier, Newton made up, he went blue and then violet. Red, orange, yellow, green, blue, indigo, blue, violet, purple. Let's not get into naming colors because that's, if you're dealing with a fellow who thinks he's well dressed. All right, anyway, so design. Light source is incident on the screen. Is incident on a diffraction grading of slit separation D. I'm going to say this once nicely. D is 1.73 times 10 to the minus 6 in meter. And the minus, 6 in a meter. Okay. The distance to the screen L and the distance from the central antinote to each resulting antinode X is measured. From this, the wavelength of light is determined. 2 meter sticks, materials, 2 meter sticks, diffraction grading, light source. So, what are we controlling here? What's never changing? Well, if we look at this carefully, you can see the diffraction grading here. It's a little hard to see, but it's right there. That's not changing. What else is not changing? The length L from the screen to the board. So you can constant 1 meter to keep the math simple. Now, what is changing? Well, what we're changing is the lasers, or the wavelength. And what's responding? Well, you tell me. Now, the procedure is pretty straightforward. Set up a laser, and we record the distance. So, setting up the red laser, let's see if we can do this without break. That's green, red. Let's do red first, because I can. Do this without breaking the laser. So there's the laser there. Hard to see. Here is the central antinode. And here is the first. So for red, now reminding you the wavelength for this is 650. I'm writing this out because God help me, some of you just refuse to freaking pay attention. 50 nanometers. The distance between them, X, is approximately 39.5. You can't see what I'm writing on the board, can you? That might be a little better for you guys. Now, that's red. Now, as the lab says, we change the wavelength. Let's go from red. Let's go to green. So we can do this without breaking the laser. There we go. There's the green. And of course, it comes in the... Oh, you shows about stop that. There we go. And they're doing this at a different angle just to confuse me. Okay, so that's just life. You learn to hate computers. Anyway, try jacking it up a little bit. Why is it doing that? Because it can. Enjoys being a poopy. All right. Now that's a little harder to see. If you can, So, lining them up. There's the center line for the green. There's the first. Oh, I'm supposed to do this first and second antinodes, aren't I? Okay. Now, there's the first antinode there. Sorry, go back and fix that. Now, if that's the first antinode, there should be a second antinode the same distance over here. It's really hard to see. I'm going to have to turn off all the lights in the room. Again. That help. Can you see it? Really, no. I can move closer. Does that help a little bit? No, now notice the distance. Okay, that's really not changing anything. There should be. Oh, yes, there is. Very faint. Know where to look. Sorry, I'm putting my hand in front of the laser. I can see the central antinode. You go over here. Right, there's the center. There's the first antinode, and you look carefully here. It's really hard to see in my hand. Ooh, that is faint. And down. Oh, there it is. Second, first. So let me measure that. To the first is 31. And the second, that is faint, is, it has to be in the friggin' way, 75. X1, X2 is 75 centimeters. Now, they're supposed to be twice as much. Yeah, life. Now, I apologize. That means I got to go back and redo the red, but whatever. Learn from your mistakes. Oh, don't be that poopy head. There we go. Come on. There's the red. There's the first. Oh, don't be that guy. Okay. Now we've changed the height, but that doesn't really matter. Now the second light beam should be, oh, way over here. Now I'm not putting, oh, sorry. My apologies. The reason I didn't notice it, because it's way over here. And you notice it's my hand here on the whiteboard. No, I'm not putting a mark on the whiteboard. So I'm going to go the other way because I can see it over here. This is my second over here. And that is a distance of, okay, that's 95 and a half. 95 and a half, 100. 106 centimeters. Okay. All right, that's interesting. Anyway, now let's do the blue. That should be spread out less. Working. And there we go. Right in the middle, just to confuse things. So there's the blue. Center. First and second. So for wavelength of used to be able to read the small writing. That is, okay, I'm getting old, I can't read that. That is 405 nanometers. Lambda is 405. Distance of the first one is approximately 23. X2 is 50. All right. So we've got distance of the grating. Oh, I forgot to write out the wavelength for the green laser. I'm going to turn the lights on because I'm getting old and I can't read paint like this anymore. I said this out loud twice, but 532 nanometers. Okay, so Shortest wavelength, the nodes are closest together. Longest wavelength, the nodes are farther apart. Now, I'm going to move this over and ignore the poopy pants because I have to have a chat with the grade 11s about that. And yes, I'm leaving it up just because I can. So, very briefly, here's the data you need. Distance between the slits is 1.76 times 10 to the minus 6 meters. 650 nanometer laser light. X1 is about 39.5, and X2 distance to the second node is about 106 centimeters. For 532 nanometer light, distance to the first node, antinode, is 31. Distance to the second antinode is 75. And for 405 nanometer light, distance to the first antinode is 23. The distance to the second antinode is 50. All right? So that should be sufficient evidence to do this lab. Now, note in the lab, it says you have to write out the procedure. So, as I've said before, briefly describe what I did. As I said, this is the sort of thing, enough description that, your little brother next year, the year after, can come and do this lab without too much trouble. Now, data table, here's your data. I need it recorded nicely. Analysis, sample wavelength calculation. Calculate, I'm telling you what the wavelength actually is. Okay, the red is 650, the green is 532, the blue is 405. You're going to calculate that. You're going to calculate the wavelength based on the distance d, L is 1 meter, and these x values. So you're going to get 6 separate wavelength calculations here. 9. First antinode, second antinode, the average. So these two numbers, so the red wavelength should be 650. From these numbers, you'll be off by a smidge. How much? All right. So you get the average, and you compare that to the actual. This is actual. The lab, you calculate it based on the x's here. State the percentage error of each wavelength of light and explain why each antinode appears as a rainbow. Now, percentage error. So you do the calculation for red, you get 648. Fine. Percentage error. What's percentage error? Actual minus theory divided by theory times 100%. Oh, and of course you can't see that. There we go. That's percentage error. Actual minus theory. Actual is what you calculate minus what you were told. You were told it is 650. So in theory it's 650. Yeah, my apologies. This is theory, not actual. Okay, so you're told it's 405 or 532 or 650. Explain why each antinode appears as a rainbow. What's happening here, it actually gets spread out a little bit with the diffraction grating. Now, it's really hard to show with a laser, but if you get a chance with diffraction grating, you wouldn't have a diffraction grating, but you might have a CD at home. So if you have a music CD or CD-ROM for the computer, hold it up to sunlight. And that is actually diffraction grating, and you'll see the light spread out. It spreads out as a rainbow. Really quite neat. So that's what I'm talking about there. It's a little hard to see. I'm not going to try showing you on this video. The camera's just not good enough. All right. State how many antinodes should have been observed, assuming largest angle of diffraction is 89 degrees. So if the most you can diffract is 89 degrees, how many antinodes should you see? So for the red, the green, and the blue, there's so many of them. Like I said, with the blue, you saw the first one here, second one. Sorry. First one, you saw the second one, you saw the third one. Should you see a fourth and fifth, do the calculations for me. And remember, I have to d sine theta over n, xd over nl. So when we're talking angle, we're using that. Don't use the small angle approximation because, yeah, that only works for 10 degrees. State one sources of error and one improvement. So what could have gone wrong, what might have gone wrong, like why are we getting a different number here? And one improvement. Besides the obvious one, you actually doing it yourself and not trusting Mr. Sutton because your partner's always an idiot. All right, that's it for me. So this is determining the wavelength of EMR, the second lab. I want you to get that done. Okay.